Welcome to this lecture, which showcases examples of bioprocesses that use third, fourth, and fifth generation feedstock, which we discussed about in the last lecture. In this lecture, we will use basic function-level block diagrams to represent value chains of generation 3 to 5 processes, using the following color code based on technology readiness level. This will allow us to assess how close or how far a process is from industrial practice. First up is generation 3 algae-based photoprocesses. Typically, these processes start with basic ingredients, namely CO2, water, and nutrients, and phototrophic organisms, most commonly microalgae and cyanobacteria. As seen in the previous lecture, either natural light or artificial light is used to drive the process as energy source for the organism. Several types of photobioreactors are used and are being developed, with here in the picture tubular photobioreactors as example. Open photobioreactors or open pond systems are also used, which are cheaper but more easily subjected to contamination. One of the main constraints to consider when using natural light is to make sure that enough sunlight reaches the reactor and the phototrophic organisms within. Light penetration is quickly becoming limiting, which often leads to quite thin reactors. This results in large areas of land needed to produce significant amount of product, as can be seen in this photo, which means the system must be capable of high productivity per footprint area. This land could be non-arable, of course. Other desirable characteristics for photobioreactors are high volumetric productivity, large volume per reactor, inexpensive both in capital and operating expenses, reliable, ease of control, and ease of recovery from contamination events. Microalgal biotechnologies has not yet fulfilled its potential and may even be controversial. Microalgae have been used to commercialize novel products, for example spirulina over the last 40 years, yet only a few commercial producers have found some success, while others have not survived. In some cases where microalgae producers have attempted to introduce green replacement products such as biofuels, animal feeds, or nutritional fatty acids, the industry have discovered that the cost of manufacturing those products via microalgal photosynthetic pathways was much higher than harvesting traditional sources or produce them heterotrophically. This can be seen in this graph for biodiesel production. This has led to further research in novel photobioreactor technology, and macroalgae technologies remain of interest as macroalgae are an extremely diverse group of organisms that can provide many different useful products and services. First of all, macroalgae and cyanobacteria can produce products that are excreted outside of the cells, such as lactic acid. Typically, they are genetically engineered to make such products. The downstream processing steps to separate and purify such products are also under development. Some phototrophic organisms accumulate starch as carbon storage. This starch can be recovered and hydrolyzed to sugars. These sugars can be used for further fermentative conversions. Lipids can also be recovered to undergo transesterification and decarboxylation to produce chemicals and diesels. Finally, the lean biomass could also be used to make and recover products of interest such as proteins. The reference on the slide is a good source to learn more about microalgae biotechnology. Offshore biorefinery for microalgae cultivation and product recovery are also being developed, which would benefit from using feedstock naturally present in the ecosystem, such as CO2, nutrients, light, and water. Another advantage pertains from not requiring photobioreactors and the large area available for cultivation. Some challenges regard the harvesting, the offshore biorefinery platform itself, as well as transportation. The first concept of generation 4 feedstock is depicted in this slide. At the top, we simply have a sugar-based generation 1 or 2 fermentation process, which produces carbon dioxide. One could capture this CO2 and convert it using renewable energy to compounds which could be fed back to the fermenter. In generation 1 and 2 fermentation, the sugar is used as energy, electron, and carbon source for production, growth, and maintenance. The CO2-derived compounds, such as methanol, ethanol, or formic acid, could in theory be used as energy and electron source needed by the cells, while the carbon contained in the glucose could entirely be used to make the products and biomass. This would allow a significantly higher product yield on sugar and a much higher carbon utilization efficiency. This has the potential to avoid CO2 emission towards the development of zero-emission biotechnologies and make generation 1 and 2 bioprocesses more sustainable. CO2 conversion could be done by electrolysis, yet this technology is still at low TRL at the moment. Alternatively, some of these CO2-derived compounds could be fermented on their own in another fermenter to make products of interest. Another concept of generation 4 bioprocesses is a conversion of organics found in waste into volatile fatty acids, which can then be used as platform molecules to make added value products. For example, organic food waste can be converted to C4 to C8 fatty acids by anaerobic chain elongation fermentation for application ranging from feed ingredients to fuels and materials. Another example is a conversion of organics in wastewater to biopolymers. Carbon and resources cannot be wasted in a linear economy anymore, so bioprocesses such as this allow to recycle and reuse valuable resources. Another concept of generation 4 bioprocesses is a direct fermentation of C1 gases. Several bioprocesses are being developed at the moment. The most advanced one regards syngas fermentation. LanzaTech is a company that has scaled up syngas fermentation to commercial scales in the last few years. The syngas they used at this scale is mainly sourced from industrial flue gases, such as from steel manufacturing, though they also tested syngas from biomass gasification. The main product they have made at industrial scale is ethanol to date. Higher product yields are typically obtained when hydrogen is in excess in the syngas, which is rarely the case in flue gases or from gasification units. Water electrolysis can be used to supply the extra hydrogen. Other gas fermentation bioprocesses are being developed. For example, some startup companies develop fermenters converting mixture of CO2 and hydrogen to products such as alcohols. Other startup companies develop gas fermentation converting mixture of CO2, hydrogen, and oxygen to either feed or food ingredients. The main challenges of gas fermentation regard gas-liquid mass transfer and safety when oxygen is present. These gas fermentation processes offer the opportunity to valorize carbon waste and indirectly renewable electricity to a wide range of products of interest, while not relying on agriculture nor on fossil resources. The fifth generation of bioprocesses offers the opportunity to directly integrate renewable electricity into a new type of fermenter. One of the concepts is called microbial electrosynthesis. Microbial electrosynthesis is an electrochemical technology in which microorganisms are capable of using electrons derived from an electrode, the cathode, to convert carbon dioxide to a wide range of industrially relevant products. Renewable energy such as solar and wind energy is used to power the technology. Therefore, microbial electrosynthesis allows the storage of renewable energy into chemical bonds as well as to valorize greenhouse gas. The abilities of microorganisms to use electricity directly was discovered in the early 2010s, and the technology has increasingly been investigated and developed since then. The main challenge towards industrial implementation is to develop novel reactors concepts that account for both microbiological and electrochemical constraints. Another concept is called electrofermentation. Similarly to microbial electrosynthesis, microorganisms are integrated into an electrochemical system, though for the conversion of sugars, sugar-derived compounds, or other organics. Several types of electrofermentation processes are being researched. The first one is called anodic electrofermentation, in which an anode electrode is used as a final electron acceptor for the microorganisms, as alternative to oxygen, for example. Oxygen sparging offers many technical and economic challenges to classical fermentation. Therefore, anodic electrofermentation may offer a solution. An electrode can also be used as an additional electron and energy source for the microorganisms in so-called cathodic electrofermentation. Similarly to generation 4 alpha, this could allow higher product yield and carbon conversion efficiency. Finally, an electrode could control the redox potential of the reaction medium and increase the product yield. This lecture allowed us to realize that the future is bright for biotechnologies, and that bioprocesses are part of the solutions that society needs for the sustainable production of commodity and specialty chemicals, fuels, feed, and food. Biotechnologies can contribute to greenhouse gas emission reduction and valorization, to the energy transition, and to a circular economy. It should be noted that other bioprocesses than presented in this lecture can be derived from the use of third to fifth generation feedstock. For example, bioprocesses can combine several concepts discussed in this lecture, such as microalgae can be used in microbial electrochemical technologies, or syngas could be valorized by microbial electrosynthesis. Thank you for your attention, and see you at the next lecture.